Okay, today we're going to graph quadratic functions in vertex form. You'll see that we're going to be looking for three things that you need to know to write an equation in vertex form. We've looked at these a little bit over the last week, and we're just going to examine where those three things come from. But here they are, all in our skeleton equation. We've got the stretch factor, and then we have the two component values, the x value and what we call the k value, that form the vertex of the parabola. So for these next two examples, it might be helpful to have your Desmos calculator out online, and you can use that to graph y equals x squared. My graph is going to just be a little sketch of that, and you'll see I've got 0, 0, 1, 1, 2, 4 up here, and that forms that basic parabola. And that's kind of a terrible parabola, but you get the idea. That's my parabola, y equals x squared. The expected values are over 1 up 1, over 2 up 4, over 3 up 9, and so on. But now we're going to use a table of values for this equation right here. And we're going to see what happens when we have x plus 3. So I'm going to put in -1, 0, 1, and 2. And I'm looking for the vertex, and you're going to see that I'm not going to find the vertex here. We're going to be off by a little bit, but let's just give this a try. -1 plus 3 is 2, and 2 squared is 4. 3 squared is 9. 4 squared is 16. And 5 squared is 25. So this is growing a lot, and we're not anywhere near the vertex. And so I'm going to plug in some numbers less than -1, like -2 and -3. And now we have 1, because -2 plus 3 is 1, and 1 squared is 1. And when we hit -3, we come up with 0. When I go to -4, I get right back to 1 again. And I'm like, well, wait a second. I've just found the vertex way down here. So we know that the vertex of this equation, instead of being right here at the origin, must be over at -3. So this parabola has moved over 3 units to the left. It might be a little bit strange to think that there's this thing that sounds like +3 in here, and you might want to move it to the right, but that would be a mistake. It's -3 that makes this overall value 0. So when it asks, how does the new, in this case red graph, compare to y equals x squared? It's 3 units to the left, or a -3. Okay, in the same way for the next problem, I'm going to sketch a really ugly y equals x squared with some expected values like 1, 1, 2, 4, 1, 2, 3, 4, and that's supposed to hit up there, and you get the idea of that parabola. But now with a -1.5, if I was to use a table of values, I can anticipate trying to make 0 by just starting with 1.5. 1.5 minus 1.5 makes 0, and 0 squared is 0. And so moving this over by 1.5 is what would be required to find the new point for this vertex. And we don't need to fill in numbers here or here, although I could go back by 1 to 0.5 and get 1, and I could go up by 1 at 2.5 and get 1, and both of those would also show up on this graph. In this example, we can see that we're going to move the graph over 2 to the right, and from our ax squared plus c lesson, this plus 4 means simply go up 4. And that's the new point, the point 2, 4, where we're going to locate the vertex of this graph. And so I draw the graph in of the parabola. Now, it may be tempting to just go along and do that on everyone. Oh, please note also that sometimes the equation is written with that additional number tagging on the end, like we saw in linear, and sometimes they jam it right up in front. Either way, it's still vertex form. Okay, in example 4, we have a similar idea going on. The -3 produces an h of 3, and think 3 minus 3 is 0. And we've got a -5 for the y value of that vertex. So we go over 3 and down 5. Oops, 1, 2, 3, 4, 5. And we're right there. And if I just kind of, without thinking, draw another graph of that normal parabola where you expect over 1 up 1 and over 2 up 4. If I do that here, I will have made a mistake because I've left out this one little item here, that negative. And those of you who are familiar with the work we did on stretch factor will notice that although my vertex is 3, and this is -5, when I go +1 or -1 from that vertex, I would expect to get -4 up here, like in my graph. Now remember, this graph is incorrect. Instead, when I plug 4 right here, 4 minus 3 is 1, and 1 squared is 1. But this negative stretches, or in this case, inverts that number from a positive 1 to a -1. And -1 minus 5 is -6. So you see we get -6's on either side, which is just a little bit further lower. And that's why the direction of this graph would actually go downward. Bye-bye, bad graph. Now we're just looking at some general functions. Here, we're not told what g of x is, but we are told that f of x is 7 less than g of x. So if g of x was, just say it was a line like this, we could find f of x 7 above that. So here's g of x, and here's f of x. F of x minus 7, and here's those 7 counts, is g of x. What's kind of strange about that is it doesn't matter even the shape of it. If I did a sine function or one of these, this might be g of x. And so f of x might be traveling above it like that. One thing that's important to notice is f of x. If you remember our rules of functions, the f of x is sort of like the value or the y of any function. So this is like taking y minus 7. And that's why we're moving this up and down. Along here, all of these points along this line are the y values after the function has been completed, and then minus 7. That gives us g of x. That may seem obvious, but it's going to become important when we look at example number 7. In example number 7 now, we're going to see that the plus 10 is not added to the function of x, but it's added to x. And so we're going to need to move whatever we graph over 10. Suppose the function was one of those strange absolute value functions. When we have f of x and we add 10, we're actually going to move this thing 10 off over to the left. And the new absolute value function, even though we're not used to seeing those v's, everything would be moved over 10 this way. And the question arises, when we were subtracting 7, why did it go up and down? And when we're adding 10, it goes left and right. It's not the negative and the positive that determine that. It's the fact that this is within the function that moves it 10 to the left. Okay, go ahead and try example 1 and 2, and then I'll have the graphs here for you to look at after you've tried them. So go ahead and pause and try those two. Okay, example 1 looks like this. Where the vertex is moved over 1. And that's because we see this x minus h. Okay, we don't have to worry about a k because it's not moving up or down. Just this h. Okay, and in example 2, we go back 1, and 1, 2, 3, 4, 5, 6, 7, and that vertex would be at -1, -7. Here's the -1, the h, and here's the -7. Notice that this is included entirely, and here this is like subtracting a -1. That's where we see that plus sign. Okay, in example 3 and 4, we're simply multiplying values, whether it's the y value, so this would be 0, 0, 1, 5, making that, oops, missing it there, and making it rather thin compared to what we would expect, because each answer is multiplied by 5. Here, be aware that that 2x is like changing the function y equals x squared into y equals the quantity 2 times x, or the product 2 times x squared. And you see this is going to make this go up rather quickly, because we have 0, 0, then we have 1, 4, and then we have 2, which would be 16, because 2 times 2 is 4, and 4 squared is 15. This also is a very, very dramatically thinned out parabola. Okay, what are the 3 things you need to know to write an equation in vertex form? Well, here's the skeleton. Come on, pen. There we go. Sometimes the k value is in front, sometimes they add it to the end, but you need to know the h and the k of the vertex, and you need to know something about what the stretch factor is doing to the shape of the parabola. Not only the shape, but the direction, in case this happened to be a negative right there. Okay, guys, good luck on that checkpoint, and we'll see you tomorrow.